Have you ever stopped to watch one of these steel beasts at work? Its size is overwhelming, its power brutal. But the result it leaves behind is quite the opposite. A surface so smooth and flat it seems impossible. Therein lies the enigma. How can a colossus weighing as much as 10 cars perform the work of a surgeon? The secret isn't just in its blade, it's in its wheels, which tilt in an unusual way. It's in its back, which sways. It's in an engineering that eliminates chaos, and this is just the beginning. Let's begin. The anatomy of a stable giant. When you watch these machines at work, you notice they weigh more than 5 adult elephants. Their roar fills the construction site, and their steel structure looks like it came from an industrial plant. But now look at the ground they leave behind. A smooth, flat, almost perfect surface, like a polished concrete slab. Therein lies the paradox that defies logic. How is it possible that a 20-ton colossus, capable of uprooting tons of earth, is at the same time a craftsman of millimeter precision? The intuitive answer leads us to its blade, but that's just the tip of the iceberg. The real secret begins much earlier, in details that go unnoticed. For example, have you noticed that its front wheels aren't vertical? They can tilt to the sides as if the giant were twisting its ankle. This seemingly strange movement is the first clue to an engineering that doesn't just move Earth, but tames the brute forces of physics. What you're about to discover is how a platform of absolute precision is built from the ground up. A story where stability isn't an accident, but a mechanical achievement. Intelligent traction, more than just an engine. Imagine the challenge for a moment. It's not just about pushing. It's about pushing with overwhelming force to cut through hard ground, and, in the next instant, gliding with the smoothness of a boat to flatten a surface without leaving a mark. If the diesel engine is the heart that pumps power, then it needs a nervous system that decides, in milliseconds, how to channel that energy. This is where the motor grader abandons all resemblance to an ordinary vehicle. Instead of a conventional transmission, inside beats a marvel called a countershaft drive. Think of it not as a gearbox, but as the tactical brain of traction. Inside this metal block, a series of parallel shafts and gear sets work in a dance of pressurized oil. Its design adheres to a clear philosophy, prioritizing operational flexibility over simple power transmission. The proof is in the numbers, which speak for themselves. This system offers 8 forward speeds and 6 reverse speeds. Why so many? Because each phase of the job demands a different approach. First gear is pure muscle power. It's the gear engaged when the blade needs to dig into virgin soil or push a massive pile of gravel. The engine delivers its maximum torque, but the machine moves forward with deliberate slowness, concentrating all its mass into an unbeatable thrust. However, the miracle occurs when the work shifts from demolition to precision. As the surface is leveled, the operator changes gears. At higher speeds, the countershaft transmission undergoes a silent transformation. It changes its ratio, sacrificing some of that brute force in exchange for increased wheel rotation speed. The machine now moves faster, but with electric fluidity. This is the key to a perfect finish. The blade, which previously tore apart, now only grazes the surface. Excessive torque at this point would create vibrations, micro ripples. The controlled speed, on the other hand, allows the blade to sweep, level and compact in a continuous fluid motion, like a painter's arm applying the final brushstroke. This transmission allows the beast to change its personality, transforming from a battering ram to an artist without the operator having to fight the machine. It is the first great pillar of precision, the ability to apply the exact amount of force at the exact moment. The hidden tracks. Trick, the articulated tandem. With power intelligently distributed, the next challenge is where to put that power. On a truck, the rear axle is a rigid beam. If one wheel hits a rock, the entire structure tilts. For a motor grader, that would be a death sentence for precision. Imagine trying to flatten a table with a wobbly ruler. The engineer's solution is as elegant as it is robust. Forget conventional axles. This is where the tandem axle comes in, the rear drivetrain that turns an obstacle into a minor inconvenience. If you could see inside the large housings that protect the rear wheels, you would find an unexpected mechanical spectacle. There is no solid axle connecting them. At their center, a set of sprockets receives the rotation from the transmission. And from that core, extending to each wheel are not rigid drive shafts, but a pair of industrial tracks submerged in oil. One chain pulls forward, the other backward, forming a positive drive system that looks like it came from a tank, but with a balletic purpose. This configuration is already revolutionary because it provides devastating all-wheel drive, a 6x4 drive that knows no slippage. But the true genius lies in what this design allows: independence. Because each wheel is driven by its own set of chains from a central point, they can move vertically almost freely relative to each other. When the left wheel finds a gap and dips, the right can maintain its position. The chassis, anchored to this system, doesn't twist abruptly. It remains level. And it is here that the system takes another step forward, toward the sublime. This tandem assembly is not rigidly fixed to the machine's main frame. Observe carefully the next time a motor grader passes over uneven terrain. You'll see that the entire rear unit, the complete tandem with its two wheels, gently sways from side to side. This is the tandem's oscillation system, the masterstroke of stability. It's not a flaw. It's a shock absorber for giants. When the machine moves forward with one rear wheel higher than the other, the entire tandem tilts slightly, compensating for the torsion and keeping the main structure, where the blade is mounted, in a nearly perfectly horizontal plane. It's as if the rear wheels were the toes of a tightrope walker, constantly adjusting so that the body, cable, and balance bar remain stable. Without this articulated rocking motion, every irregularity in the terrain would be transmitted like a whiplash to the frame, and the blade would trace the outline of every bump on the ground. With it, the blade floats above the chaos, ready to impose its order. Steering and articulation. The dance of steel. We have then a machine that modulates its power and keeps its back level on any terrain. But a stable platform is useless if it can't move with agility and precision. A construction site isn't an endless runway. It has curves, edges, and tight spaces. This is where the motor grader performs its most characteristic movement, the one that distinguishes it from any other machine. It doesn't turn, it folds. To understand its maneuverability, we must abandon the idea of a single chassis. The motor grader is composed of two halves: the front module, with the engine and cab, and the rear module, with the tandem axle. And in the center, there isn't a rigid joint, but a monumental articulation. A steel pin as thick as a tree trunk acts as a pivot. On either side of this breaking point, two enormous hydraulic cylinders act as muscles. When the operator engages the steering, these cylinders don't immediately turn the front wheels. The first thing they do is push or pull to fold the machine at its waist. This is the magic moment. The motor grader articulates, reducing its turning radius to half of what it would be if it were rigid. The benefit is palpable. Imagine it needs to shape the ditch right at the edge of a road. In a long, rigid vehicle, the rear end would roll off the edge, destroying what's already been built. The motor grader, on the other hand, can bring its front half close to the edge, articulate, and have the blade work in the ditch while its rear half, the tandem axle, prudently remains on firm ground. It's a choreography of spatial precision. But bending isn't enough. The front wheels, of course, also turn. And its steering system is another statement of principles. There's no mechanical steering wheel that can be forced. The command is given, but the execution is carried out by two dedicated hydraulic cylinders connected to a steel arm called a tie rod. This rod is the guardian of the geometry. In a car, a large pothole can throw the steering wheel off. Here, when the blade encounters fierce resistance that tries to push the wheels sideways, the tie rod distributes the load between the two cylinders, maintaining the exact turning angle the operator commanded. The steering doesn't deviate even a millimeter. It's an unbeatable combination. The central articulation for tight turns and the reinforced hydraulic steering to maintain course under fire. Together, they transform a 9-meter-long vehicle into a machine capable of carving perfect curves in the mud. The secret tilt of the wheels, overcoming drift. We've built a powerful, stable, and maneuverable foundation. But one subtle, persistent force remains that can ruin everything: lateral drift. Think about basic physics. When the blade, positioned to one side of the machine, digs in and pushes a load of earth to the right, it applies a colossal force. According to Newton's third law, That action generates an equal and opposite reaction. The entire machine therefore receives a push to the left. It's like trying to cut a steak with a dull knife. The knife slides instead of cutting. On soft ground, the front wheels would give way, the machine would veer off course, and the cut would lose its precision. On a slope, this effect is magnified, dragging the behemoth downhill. This is where the most distinctive and critical movement comes in, the one that answers the initial question, the tilt of the front wheels. Take a close look at the next pass. When the blade is loaded with material and working, for example on the right side, you'll see that the front wheels aren't vertical. They're tilted several degrees to the right, in the same direction the dirt is being ejected. This isn't a cosmetic adjustment. It's a matter of pure engineering. By tilting the wheels, their contact patch with the ground is dramatically altered. The tire no longer makes full contact with the ground across its tread. Instead, the outer edge of the rim, reinforced and often with a more aggressive profile, digs into the terrain. It's the equivalent of a soccer player digging in their cleats to change direction, or a skier edging their skis to carve a turn in the snow. That tilted rim becomes an anchor, a pivot point that vehemently resists lateral slippage. The force trying to push the machine to the left encounters formidable resistance generated by the very tilt of the wheels to the right. The result is that the 20 tons of steel maintain a straight, unwavering trajectory, while its arm performs a monumental torsional feat. A simple hydraulic cylinder is responsible for this ankle turn, a movement that transforms a potential weakness into its greatest strength. The artist's arm, where strength becomes precision. All the engine's power, all the chassis' stability, all the intelligence of the drivetrain now converge on a single point, the blade assembly. But calling it a blade is a dangerous oversimplification. It's not a tool. It's a 6-stringed instrument, where each string is a distinct movement, controlled with Swiss watch precision and protected by mechanisms worthy of a safe. Here, in this space between the frame and the ground, brute force ceases to be a hammer and becomes a scalpel. And it all begins with a joint that seems too simple for the task at hand. The drawbar and the magic ball, the connection that holds it all together. All the machine's thrust, the hundreds of horsepower, the mass of thousands of kilograms in motion must be transmitted to the blade so it can cut. And this flow of force has a deliberate bottleneck, the drawbar. Imagine a robust, A-frame-shaped arm bone extending from the front of the chassis. It's the connecting link. But at its front end, where it joins the rest of the blade system, there's an element that looks like a toy, a solid steel ball, about the size of a medicine ball. This ball is the universal connection point, and its spherical shape is the key to everything. Think about the stresses it's subjected to. The blade doesn't just push forward. When it encounters a rock, the force is a sudden impact. When working on a slope or with the blade turned, the load is lateral, a torsional force. If this connection were a simple rigid pin or a conventional joint, it would break within hours under that multi-directional stress. The ball, on the other hand, absorbs it all. Housed in a spherical cup, it can pivot, rotate, and oscillate in any direction, allowing the structure to move naturally under load without creating points of concentrated stress. It's like the joint in your shoulder, allowing you to move your arm through a full circle. This ball literally does all the work. It's so critical that it's designed to be replaceable, held in place with bolts that allow it to be swapped out when wear is inevitable. It's the first and most humble genius of this system, a sphere that transforms monolithic thrust into organic movement. The turning circle, the clockwork mechanism beneath the blade. Anchored to that magic ball, the real choreography begins. Between the drawbar and the blade itself lies a massive circular component, the turning circle. It's a toothed ring, a giant gear that looks like a cog from a clock tower. Its function is obvious and vital, to allow the operator to rotate the entire blade, orienting it at any angle relative to the machine's movement, from 90 degrees to dig a side trench, to just a few degrees to put the finishing touches on a curve. But what happens to achieve that rotation is one of the most elegant and decidedly ingenious mechanisms in all of heavy engineering. Beneath that toothed ring, there isn't an ordinary motor. There's a hydraulic motor that drives a worm gear system. Imagine a long screw, like a wood screw, but with helices that mesh perfectly with the teeth of the upper gear. When the motor turns the worm gear, it, with a slow but incredibly powerful movement, pushes the teeth of the gear and makes it rotate. So far, it's robust engineering. But the magic lies in a physical property inherent to this design. It's intrinsically non-reversible. What does that mean? It means that the crown, no matter how much force it receives from above, for example, if the blade strikes an immobile rock, is physically incapable of turning the worm gear in the opposite direction. The angle of the teeth and the friction prevent it. It's a mechanical dead end. This is a boon for precision. When the operator positions the blade at a 45-degree angle to form a slope, they can be absolutely certain that no matter how hard the earth pushes, the blade won't move an inch from that position. The mechanism is self-locking. It's like having a ratchet built into the machine's core. This design protects the hydraulic motor from sudden impacts and gives the operator an infinitely stable working platform. The blade becomes a steerable anchor firmly fixed at the angle the operator has chosen. The slip clutch, the fuse that saves the watch. But top-level engineering always considers the unthinkable. What if the impact is so catastrophic, so brutally exceeding any calculation, that even the worm gear's shielding could fail? A direct hit against a buried rock at full speed could, in theory, transmit such monstrous torque that it would shatter the teeth of the crown or the worm gear itself. For this nightmare scenario, there is a second shield, a mechanical fuse designed to sacrifice itself, the slip clutch. This device is located in the rotation transmission line. Basically, it is a stack of steel discs pressed together by the action of precisely calibrated springs. Its function is to transmit the motor's rotation to the watch, but only up to a predefined torque limit. Those 3 adjustment bolts visible on its housing are what establish that limit. It works like this. Under normal conditions, the friction between the discs is enough for them to rotate together, transmitting all the movement. But when the violent impact occurs, the torque attempting to recoil overcomes the spring force. In that critical instant, the discs slip. They rotate against each other, releasing the tension with a controlled squeal. It's a deliberate sacrifice. The clutch wears down, absorbing the impact energy that would otherwise travel straight to the precious and expensive worm gear mechanism. After the event, the operator simply needs to check and, if necessary, readjust or replace the clutch discs. A relatively simple and inexpensive operation. It's a passive, elegant, and redundant safety system. First, the non-reversible design slows the attack. Second, the mechanical fuse is sacrificed if the attack is overwhelming. 2 lines of defense to protect the heart of precision. The 6 degrees of freedom, how the blade, really, moves with a ball joint, supporting everything and a shielded pivot mechanism. The blade is ready for its ballet. And it's a ballet with 6 fundamental movements, 6 degrees of freedom that make it the most versatile tool on a construction site. The first and second are obvious. Up and down. This is achieved by the 2 large lift cylinders, which raise or lower the entire drawbar and circle assembly. This controls the depth of cut. The third is the blade pitch. A cylinder tilts the upper blade support forward or backward. Tilted backward, the edge becomes aggressive, biting into the ground for a deep cut. Tilted forward, the edge flattens, ideal for spreading material or providing a surface finish without penetrating. The fourth is the side shift. Another cylinder moves the entire blade, along with its circle, to the left or right of the machine's central axis. This is crucial. It allows, for example, smoothing the edge of a road without the machine's wheels hanging over the edge. The blade extends, the chassis remains on firm ground. The fifth movement is the circle, governed by the magnificent worm gear mechanism we've already explained. This allows the blade to be positioned at an angle for digging trenches, forming slopes, or continuously pushing earth to one side. And the sixth, an extra and strategic movement, is the reach adjustment using the link bar. This is a bar with multiple holes in the front frame. By changing the position of a pin between these holes, the geometry of the entire arm is altered. In the center position, it's standard. In the side holes, the arm is virtually lengthened or shortened, allowing the blade to work much further from the side of the machine or to achieve a more aggressive angle of attack for extreme slope cuts. 6 movements. Countless applications. From the straight and superficial pass to the complex and deep cut, it's all in the operator's fingers. From steering wheel to joysticks, the fighter pilot's cockpit, decades ago, taming this 6-degree of freedom beast was a physical feat. The cab was a forest of metal levers, each connected directly to a hydraulic valve by rods. Moving the blade required considerable strength, pinpoint accuracy, and superhuman coordination. It was backbreaking work. The silent revolution changed everything. Step into the cab of a modern motor grader. The first thing you notice is the relative silence and the absence of that steel forest. In its place, flanking the comfortable operator's seat, are 2 ergonomic joysticks, like those on a high-end video game console. These 2 controls are the digital command center. With slight movements of the thumb and forefinger, the operator controls each and every one of the blade's 6 degrees of freedom: steering, center articulation, and transmission. A gentle sideways movement of the left joystick moves the blade. A twist of the wrist on the right tilts it. The electronics translate that minimal command into a signal that travels to ultra-fast response hydraulic servo valves, which in turn meter the oil flow to the cylinders with a smoothness impossible to achieve mechanically. The old steering wheel has also disappeared in many models. Steering is integrated into a lateral movement of one of the joysticks. This isn't just about convenience. It's a quantum leap in precision. It reduces fatigue to 0, allows for infinitesimal corrections on the fly, and transforms the operator into a true precision driver, where their intention translates into machine movement without friction or resistance. Along with panoramic visibility cabs that eliminate blind spots, the operator has a direct, fluid, and total connection with the machine and the terrain. The beast has been tamed, and its reins are digital. The counterattack, rippers, chains, and the battle against the terrain. Even with all this power and control, the terrain sometimes puts up a fight. For those situations, the motor grader doesn't come unarmed. It has an arsenal of tools and tactics to counterattack. At the rear, the ripper is often mounted. It's a frame with several steel teeth, like giant fangs, powered by a hydraulic cylinder. While the blade is for cutting and spreading, the ripper is for destroying. It digs into compacted soil, loose rock layers, or old asphalt, fracturing it and preparing it for the blade to work on next. It's the giant's can opener. For treacherous, soft, or muddy terrain where the wheels would slip and sink, there are anti-slip chains. These are heavy-duty mesh chains that fit over the rear tires. They multiply traction by creating hundreds of extra grip points, preventing the wheels from digging in and allowing the machine to maintain its thrust even in mud or loose sand. And we can't forget the front counterweight, that solid block of steel visible on the machine's nose. Its function is crucial during asymmetrical work. When the blade is extended and fully loaded on one side, it exerts an enormous torque that tries to lift the front wheel on the opposite side. The counterweight acts as ballast, counteracting this effect and keeping the front wheels firmly planted on the ground, guaranteeing traction and directional stability. Without it, the machine would twist dangerously. At the end of the journey, the picture is complete. We no longer see a machine, we see a symbiosis. A chassis that is an articulated and stable fortress. An arm that is a precision instrument protected by mechanical ingenuity. And a cab where human will is translated without loss into the movement of hundreds of kilograms of steel. The initial paradox is resolved. The perfect flatness doesn't arise from delicacy, but from the absolute mastery of force. Every vibration is dampened, every lateral reaction counteracted, every impact absorbed. The grader doesn't fight against physics, it plays the orchestra. In expert hands, it becomes an extension of the operator's body and mind. It's a 20-ton paintbrush, where the canvas is the earth and the paint, the transformed terrain. Then, the inevitable question becomes personal. Faced with this ballet of power and precision, where human engineering masters the most brutal elements, would you dare to take the controls of this giant, to feel how your decisions become perfect geometry on the ground? The answer perhaps lies the next time you see one at work, and you can no longer see just a machine, but the complex and beautiful extension of a will.